All right, good morning. This is physical science. I'm sorry. This is linear algebra. I'm off into the afternoon already. I just wanted to let you know a couple of announcements before we got started today about office hours. And things probably changed since Tuesday when I left, probably a similar announcement. Today, normally on Thursdays, I have Tuesdays and Thursdays, office hours 12:15 to 3:15. Not today, not Tuesday, not next Thursday. Here's the adjusted. After this class is over, we'll go down and eat lunch and probably come back about 1:15 or so, and we'll have makeup class for differential equations because next Tuesday I've got a doctor's appointment. So I won't be in the office. I'll be in the office from 12:15 till about 1:15. Then I will make up the class, differential equations class. That'll go 1:15 to 2:30. Then I'll be back in the office from 2:30 till 3:15. So that's my office hours today. Tomorrow, not on either campus, anytime. I've got an infusion in the morning. Have to be there for labs at 6:30, infusion at 7:30, and it's probably going to be a 7-hour job. So won't be on campus at all tomorrow. Monday will be normal again. Tuesday, however, I've got a doctor's appointment at 8 o'clock. Hematologist only sees patients on Tuesday morning, so I can't get out of that one. And I hope to be back on campus for this class on Tuesday. So plan to be here at 11 o'clock on on Tuesday. But then, normal office hours were 12:15 to 3:15, not Tuesday, because my first class that I missed, the 8 o'clock class, we're going to do that makeup class at 12:30. So that'll be 12:30 to 1:45, so I'll not have any office hours until 1:45 until 3:15 on Tuesday. Wednesday will be normal. Thursday, however, I've made up all the classes, all that kind of stuff. However, we have a faculty meeting Thursday afternoon. That's not tomorrow, but not today, but 1 week from today. And that will be from 2:30 until 3, well, I'm leaving it before 3:15. So my office hours on Thursday, 1 week from today, will be 12:15 to 2:15, because I'll leave about 2:15 to go to the meeting at 2:30. Then, Friday of next week, no infusion, but it's Veterans Day. So it's a state holiday. There's no classes, the campus will be closed all day Friday. Next week, this week it'll be open, but I won't be there. Next week it'll be closed, and I won't be there either. Okay, enough of that. Any questions before we get going today? All right. I think last time we did the definition of linear dependence and linear independence on the bottom of page 173. We were ready to do example 7. Is that where you got it? Yeah. Okay. So example 7 says, here's a set. Well, let me get my pen back to black. Okay. Here's a set. S. This is a set of ordered pairs. The first of these is 1, 2. The second of these is 2, 4. That's the set. That's the set in R2, the plane. Is that linearly independent or linearly dependent?
Well, they're multiples of each other.
Therefore, they're dependent. One depends on the other, one's twice the other. So that's linearly dependent because -2 times the first minus 2 times 1, 2 plus 2, 4 is equal to 0. Okay? That's a 0 vector, 0, 0. Okay? And for that to be the case, if they were linearly independent, The only coefficients that would make that happen is if all the coefficients were 0. Here, the coefficient is -2, there the coefficient is 1, but you still get a 0, 0. So, linearly dependent. That's the A, sorry. The B. Here's a set, S. It's a set of, sorry, set of ordered pairs, 1, 0, 0, 1, -2, 5.
Okay, so it would be -2 times the first one.
All right.
Plus
That's also
5.
linearly dependent. Yeah, because actually 2 times the first, 1, 0.
Oh, yeah, do 2 times.
Yeah, I mean, you could do it the other way too, but it's a little easier this way.
Plus
-5 times the second, plus the third,
plus
equals 0, 0. Okay. Now, I'm going to jump a little bit ahead here. And you knew that was linearly dependent because you're in 2 space and you have 3 vectors. There's no way. And in fact, the first 2 of those is your standard spanning set for the 2 space. So any other vector is going to be some multiple of that. It has to be because that's the definition of the spanning set, really. So, yeah, no way. If you're in 2 space, could you have 3 vectors that are not linearly dependent? Okay? Now, C. Okay. Here we have a set S. They love S, don't they? And that is the set 0, 0 and 1, 2. Okay. What do you think that is? It's NR2. The other one I should have put that. It's what?
independent.
Nope. Linearly dependent too. And here's why. Anytime you have the 0 vector in,
Oh, you can multiply it by anything.
exactly, and have the second one be 0, you could have 7,485,123 times 0, 0. Sorry, where is that? Okay, it didn't show up. Okay, plus 0
So
times 1, 2.
beats all.
Yeah, right.
Is there any one of these that would be independent?
None of those.
Like, I mean,
This would have been independent. Okay.
that would have been.
Yeah, if you left this one out, that would have been independent. In fact, this one I think would have been independent. Yeah. Okay. Leaving that one out, or leaving that one out would have been independent. But having 3 in a 2 space, no, it's not. Okay. That would have been independent if that second vector would have been a 2, 5, or a 2, 3, or a 2, 2, you know, or a 2, 1, or 2, 0, blast off, you know, it does, yeah, it could be, but not 2, 4, okay. This one, if that would have been a 1, 0, or a 0, 1, you know, but not with the 0, 0. Okay. Okay.
2 2s and
I chose a
rockets.
pretty hard, huh?
2 2s and rockets.
Yes, exactly. Simpler, we could have said 1 times 0, 0 plus 0 times 1, 2
Yeah,
would be the
just
0, 0.
short 7,485,123 to 7. So
Yeah, it wasn't necessary, but I did it anyway. Okay.
we like to be,
All right.
we like to exaggerate,
At times. Okay. Now, they say at the bottom of the previous page, the next example demonstrates a testing procedure for determining whether a set of vectors is linearly independent or linearly dependent. And here's what they're suggesting. Determine whether the set of vectors in R3 is linearly independent or dependent. Here, well, let me get to a clean page. Okay. Here's your set S. This is V1, V2, V3. Okay. And these three happen to be ordered triplets in R3, 1, 2, 3, 0, 1, 2, and negative 2, 0, 1. Seems like we've seen these before. They seem to like to use the same one over and over and over again. Okay. Now, to test for linear independence or dependence, you form the vector equation that you would expect to have C1 times 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times negative 2, 0, 1. And you see if that can equal to 0 vector. Okay? I wrote it out. They wrote it just as a 0 vector. Okay, whichever way you want to do it.
This looks familiar.
Yeah, very. Okay. And that basically says,
Talking about the format.
yeah, C1 minus 2C3 is equal to 0. 2C1 plus C2 is equal to 0. And negative 2's, oh, I'm sorry. Lost here. 3C1 plus 2C2 plus C3 is equal to 0. Okay? So get your good old matrix here. 1, 0, negative 2, 2, 1, 0, 3, 2, 1. Okay? And see if we can well, a couple ways you could do this.
Yeah, I've seen this one before.
Mm-hmm. And what do you do? Simplest way to check. I think it's the simplest. You can
It would be the determinant.
Yes, you can do the determinant. That's what I was going to say. You can do several things. You can row reduce and see if you get a row of zeros at the bottom. If you do, that's not going to work. If you don't, it will work. Okay. In other words, you're checking to see if this is an invertible matrix. That's what you're checking.
If the determinant is 0, we can just
Then it's not invertible. Yes, exactly. So let's do the determinant. And what would that be?
Okay, let's see. 1
1
plus a negative 2 times 4 minus 3, which is 1.
and that's going to be negative 1. Which, who cares what it is, it's just not 0. And if it's not 0, you do have, now,
We can go further with the problem. No.
every other time they said just do the, find the determinant. And that's all you need to do. But this one, they said, no, let's do the row reduction. And when you do it, you find out the only possible solution for that is C1 equals 0, C2 equals 0, C3 equals 0. Okay.
So if it is 0, it has a singularity, which means there is a C1, C2, C3 that can make that equal to 0 that's not 0.
Right, exactly.
So this is actually, if we don't find 0, it's an easy problem.
Right.
And then, well, I mean, it's easy, it's shorter than if we
Yeah,
find
right,
out that
Exactly. So, that's, before they did the determinant, when we were doing the row reduction. This time they did row reduction. We did a determinant. Gives you the same result. If all you're doing is testing whether it is or not. Yeah. Okay, so here is the what they're suggesting. Now, the thing that irritates me about this one is that no, it's not quite. On first glance, it almost seems like you write the coefficients as you see them in the if you'll notice this, what you have there as your three vectors, rather than write those as column, as row vectors and augment those, write them as column vectors and augment those, and you have that's your matrix that you're interested in doing. Okay, and because you see the first one right, that is a column, second is a column, third is a column. So transpose. You transpose, yeah. Well, you see, they weren't really ever a matrix, but if you wrote them as column vectors and partition them, put them together, then that's what you have. But don't write them as a row vectors, because that won't work. You want them as columns. Okay. That was just sort of an aside. So this summarizes what we just did, is testing for linear independence and dependence. If you have a set S of vectors in whatever kind of space you got, V1, V2, V3, dot, 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 up to V sub k, whatever your k might be, it's a set of vectors in a vector space V. Okay? To determine whether it's linearly independent or dependent, use the following steps. First, from the vector equations, C1, V1, plus C2, V2, plus C3, V3, plus dot, 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 plus C sub k, V sub k, okay, equal the zero vector, okay? But this is the test. Can you come up with a set of constants there that will produce a zero vector? You always can. All zero C's will give you the zero vector, guaranteed. If you can come up with any other combination, even if one of them's not a zero, then they're linearly dependent, okay? The only way this would work if all the C's were zero, for it to be linearly independent. So this next step is use Gaussian elimination to determine whether the system has a unique solution, okay? Now, if all you're doing is you can either do Gaussian elimination, or you could do take a determinant if that tends to be easier. So use Gaussian elimination to determine whether the system has a unique solution. Okay, that's one way to do it. You could just do a determinant if that's easier. Number 3, okay? If the system has only the trivial solution, C1 equals 0 equals C2 equals C3 equal dot, 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 all the way up to equal C sub k. If that's the only solution, then S is linearly independent. If the system has a non-trivial solution, a non-trivial solution, then that implies S is linearly dependent. Okay. Now, there's another little linear algebra applied here. Image morphing, process by which one image is transformed into another by generating sequences, synthetic intermediate images. The morphing has a wide variety of applications. Movie special effects, wound healing, cosmetic surgery results, simulation, aging, as in a missing child, and 5 years later, what does that child look like? Any of those kinds of things. Age progression software. Morphing an image makes the use of a process called warping. You almost make them sound like they rhyme. In which a piece of the image is distorted. The mathematics behind the warping and morphing can include forming linear combinations of linearly independent vectors that bound a triangular piece of an image and performing an affine, or affine, I think is how you say it, there's no L in it, affine's transformation to form new vectors, and the image piece that is distorted. So I guess what they did here is start out, it looks like the left half is, I would almost guess a woman's face, but it doesn't have to be, I guess. But you sure hope the right half is a man's face. I mean, I hate to see a woman that way. Never mind, I didn't say that, did I? All right. But there's lots of applications there. Oh, and by the way, I did talk with Karen about the possibility, and she said she couldn't think of anything right now, but she would sort of keep her eyes out for something. She's got a couple new projects, and I said, if you got any manipulation of a data set, something that, I'll think about it. So I figured you'd probably do about anything like that. Oh, her question was, how long would you have to work on it?
Wow.
Yeah, that's sort of the key thing. I mean, you have so many hours a week, every week, or you only have it for a few weeks. I mean,
I'd guess and say, there's really no limit.
right. Well, I would think you'd need it done by May or something, wouldn't you? Not necessarily.
Probably be good to have it done
Before May, right. Right. And how many hours a week could you?
I'm not sure.
Yeah, I know. That's why I thought, wow, you're already pretty nailed down. Why I thought of it. I was thinking, I wondered if something like this would be something you'd be interested in, a paper topic, but then I thought it would be
a pretty neat thing.
It is. It really is.
It's, the way video software and that sort of thing works is everything's broken down into triangles.
Yeah.
It's kind of interesting how they kind of fill in the blank.
Yeah.
Vectors.
Yeah. It makes me think of it's a randomness thing. I can't think of the term for it now, but that you so close and I just can't get to it. There are little bits that you just change a little thing on it and you come up, it's like chaotic motion type thing. Just a little bit of a, I'll think of it sometime, but I can't get it now. All right, example 9. Determine whether the set of vectors in P2, so now we're going to polynomial space here. So let's start with new slide here. This set of vectors in P2 is linearly independent or dependent. Here's your set, S, but this time you've got polynomials. The first of these is 1 plus x minus 2x squared, comma, second one being 2 plus 5x minus x squared, third one being x plus x squared. And we're calling this vector 1, this vector 2, and this vector 3. Okay.
So we need to set all of that with
Yeah.
C1, C2,
Some C1 times 1 plus x minus 2x squared plus C2 times 2 plus 5x minus x squared plus C3 times x plus x squared. Can you set that equal to the 0 polynomial? Okay. Certainly you can if all three, C1, C2, and C3 are 0, that works. Okay. Let's see if there's another one that might work.
Well, so we won't put this in a matrix.
Yep.
Can we skip the whole rewriting it and just
Right. If you want, choose B1.
that would be 1, 2.
Are you going down or across?
I'm going down.
Good. 1,
2, 0.
2, 0. That's the way to go there.
1,
1,
5,
5,
1,
1 there.
2.
Negative 2.
Oh, it isn't. Have a plus. Wait. I've copied it.
Oh, did I copy it right?
No,
Okay.
you copied it right.
Okay.
I need to make a check. All right. So then -1 and then positive.
Okay. Okay, and you could augment that to zeros, but who cares? That's not going to change anything. What you're interested in is what this does.
Okay, so we're going to take the determinant of that.
If you choose,
We'll do the bottom row.
I like it.
All right. So that would be 1 times -1 is -1.
So negative 1, and then do that minus 1 plus 4. Okay.
No, it would be plus. It would be 3. Right?
Negative 1 plus 4 is, 3. Okay. Plus 1, and then I'm going to get these off of there. So, oh!
That would be 3 again.
Okay. Yuck, it's not erasing. Okay. I don't have to do that, but I choose to, and that would be
5 minus 2, which is 3.
is 3. Okay. Well, that's minus 3 plus 3.
That is 0.
That is 0. So the answer is linearly dependent. Okay. Now, is there any more they really want there?
Is it?
I don't think so. This implies there's infinitely many solutions. So the system must have a non-trivial solution. You can conclude that the set is linearly dependent. Okay, and then they come up with one. So if you really needed that, we would have to do the Gauss elimination.
So
If
that
you
would
just
be show a solution.
Huh?
It would be show a solution.
A non-trivial solution. If that was the question, then go on and do row reduction. But if it's just saying does it or not, the determinant tells you that. Okay?
Number 10.
Number 10. Let's clear this. Okay. Determine whether the set of vectors in M22 space is linearly independent or dependent. So here's your S. This time it's a set of 2 by 2 matrices. The first one being 2, 1, 0, 1. The second one being 3, 0. Whoops. 2, 1. Ah, why am I doing that? And the third being 1, 0, 2, 0. Okay. If you were to do this, that would be C1 times the first one, 2, 1, 0, 1, plus C2 times the second one, 3, 0, 2, 1. If I wrote it right. Yep. Plus C3 times the third one, 1, 0, 2, 0. We wonder if that can be the 0 2 by 2 matrix.
So we're going to turn this into a bigger matrix to test and see.
Yeah. Yeah, what you do, it won't be square. Yeah.
Oh, so we won't be able to.
Yeah.
Okay, so 2, 3.
Which you're going down or across? Okay, across.
Oh, that.
All right, I wrote.
2, 3, 1.
I know. I said.
Would it be across or down?
Huh?
That would be across, wouldn't it?
Yeah.
Okay.
Yeah. That's why. Okay. Before I heard what you said, I was going to ask which way you're going. 2, 3, 1.
And then 1, 0, 0.
All right.
0, 2, 2.
Okay.
The order really matters.
Now, in this one, you can't take a determinant, not square. So this, you have to do a row reduction.
Let's
Okay.
do some switching here.
And guess what? First thing I want to do.
Move the first row to the bottom.
Yeah. Well,
Switch the second row with the
first row. Yeah. That you could do the other. I want that second row on top.
Yeah, I thought you.
Okay. 1, 0, 0, and then whatever else, it doesn't really matter. 2, 2, 1, 0, 2, 2, and 1, 1, 0. Okay. What are you going to do next?
Where? I think it's 3.
Oh, wait, there is a 3 somewhere,
Yeah,
isn't
that,
there?
that middle 2 in the top row, and then the second row
Yeah.
is a 3.
You know, I thought I had a 3 there, and for some reason I
That's
changed
I thought something was squirrely.
it. Okay. Got it. Okay.
Okay, so everything below that needs to be zeros.
Okay.
-2 row 1 plus row 2.
Okay, so that's a 1, 0, 0.
Plus row 3.
And what you say, minus row 1 plus row 3? 4.
Row 4.
4. Okay. Okay, so you get a 0.
1, 0. And then for the second row, oh, you did that. Okay, yeah, that'd be 0, 3, 1.
Right?
And then your middle row doesn't change. And then you get 0, 1, 0.
Yeah. Okay.
Now I'd say let's switch the fourth row to the second row.
Right, why not? Okay, I don't know if I'm going to have room to do all this, but I'll erase things if I need it. 1, 0, 0. 0, 1, 0. I'm just going to drop the other 2 down. Is that okay? 0, 3, 1.
That's exactly what I did.
0, 2, 2. It doesn't matter. You're just moving. Okay.
Alright, so negative 3, row 2 plus row
Yeah.
3.
Yeah. Okay.
And then negative 2, row 2 plus row 4.
Okay. I think what I'm going to do here is do some erasing. I guess I got to erase the set. So I know I'm going to regret that, but I can always look it back up. Okay. We'll see if that will suffice for now. Okay. A 1, 0, 0, 0, 1, 0. What's your new third row?
0, 0, 1.
1. Yep.
And then the last row 0, 0, 2.
0, 0, what?
2. Well, that looks pretty reduced to me.
Yeah. And really all we have to do is Gauss elimination. And we did. We didn't do any Gauss-Jordan.
Wait.
But we wound up with this. But,
You can double row 3 and add it to row 4 and get row 0.
right. But the thing is that going to, you still have a unique solution here. Because all you have is 3 variables. And that fourth row is just sort of extraneous. Okay? Ooh. Shows that it has only the trivial solution, which means it is linearly independent. Because you get this row here. And you only have 3 variables. The fourth row is not necessary because it's just extra, you know, in a sense. If that third row
Was the row 0?
was row to 0, then you got, yeah, then it's linearly
Multiple solutions.
dependent. Now, here is there are circumstances nah, I don't think there are. I was going to say we've been sort of ignoring that extra column out there, the 0, because that's what you're wanting to do. I'll add the 0. But you're only interested in this part. That really doesn't enter the picture in here. So I'm not going to say that before, but I thought maybe there's a circumstance. Not yet. We're not going to mess with it. Okay. Now that was example 10. Linearly independent. Okay. Here's example 11. Okay. Determine whether the set of vectors M41 is linearly independent or linearly dependent. Here's your set. Set of these vectors, V1, V2, V3, and V4. And they actually give them to you. And that's the set of column vectors 1, 0, negative 1, 0, comma, 1, 1, 0, 2, comma, 0, 3, 1, negative 2, comma, 0, 1, negative 1, 2. Okay, I hope I got those right. Looks like I do. Okay. Oh, man. Is there a set of C1 times 1, 0, negative 1, 0 plus C2 times 1, 1, 0, 2 plus C3 times 0, 3, 1, negative 2 plus C4. Did I miss one?
No, I missed one.
Okay. 0, 1, negative 1, 2. That's equal to 0, 0, 0, 0.
See, I only wrote 3 vectors, and for some reason I missed the last one.
All right. So this will be all right. Burr. Right?
Yeah.
Okay. 1, 1, 0, 0, 0, 1, 3, 1, 0, 1, 1, minus 1. Okay? 0, 2, 2, 0, 2, negative 2, 2. Oh, man. Wish I had an ice cream to warm up to. Okay.
Ice cream.
Yeah, it's not that cold. I used to say that in Nebraska. Need to stop by the dairy store to get ice cream to warm up, you know, because it could get really cold there.
When it's below freezing, that's funny.
Yeah. Of course, most of the time that was at night, and then the dairy store wouldn't have been open. But, you know, still, I can remember walking home one night after finals in December,
Oh man.
and it was negative 15 when I got in.
You were walking home.
Walking home, my mustache froze. My breath, and maybe looked like breath with snot, but you know, anyway, it froze.
Condensation from your
Little ice cubes hanging on the things. Okay. All right.
That's too cold for me.
It was too cold for me too. Minus row 2 plus row 1. And down here, minus row 2 plus row 3. Right?
Oh, you're doing row 1 as well?
Oh, that's right. We don't have to. All we need is Gauss. Okay. Minus 2 row 2 plus row 4. No. 3 and 4 look so close, but not quite. Okay. So we're leaving 1 alone, 1, 1, 0, 0. Leaving 2 alone, 0, 1, 3, 1. A good defense, by the way, on basketball. Okay. So, okay. And then the next one would be a 0, 0, negative 2, negative 2. And the third one would be 0, 0, negative 5. Wait. It'd be a negative 6 minus 2. 8. Okay. And that would be, 0.
And then just half of row 3.
Okay. You could do that.
Negative 1/2.
Yeah.
Both even.
Yeah.
2.
Yeah.
Right.
That would do okay. What I was thinking was divide row 4 by negative 1 and flipping it with row 2. row 3. But either would work.
Oh, because you need to have a 0 after it.
You don't have to, but that would make it easier to do it the last one. It doesn't really matter. Yeah. Yeah. So, yeah. -2 into that, so that's going to be a 1, 1. I think I'll just change those. Because I didn't want to write all that over again.
Can't blame you.
Okay. And then finally,
Oh, I see
8.
what you're saying. Yeah, we probably should switch those two. Because that way the big one's all the way down the diagonal.
Yeah. But, yeah.
So we could go ahead and switch that and divide the last row by -8.
You know, you mean flip them, now, like I said before, and do that?
Not that order.
Right. Okay. Divide by -8, the last row.
And then flip the bottom 2 rows.
Right. But you're still going to have to eliminate the 1.
Well,
Yeah.
well, we can do that.
Okay. So 1, 1, 0, 0, 0, 1, 3, 1, 0, 0, 1, 0, and 0, 0, 1, 1. Is that what you're meaning?
Yeah.
Okay. And then minus row 3 plus row 4, right?
I kind of took a shortcut and just wrote
Right.
it.
Yes. Okay. And that would be 0, 0, 0, 1. Yeah. Okay. So that one would become a 0.
So this is independent.
Linearly independent.
And
Exactly.
only the trivial solution exists.
Yeah. That's only true. Okay. Now, a little block there, starting a new thing. If a set of vectors is linearly dependent, then by definition, the equation C1 V1 plus C2 V2 plus C3 blah 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 up to CK VK equals 0 has a non-trivial solution. Okay. Good, scratching my nose itches. A solution for which not all the C's, I's are 0. For instance, if C1 is not 0, then you can solve that equation for V1 and write V1 as a linear combination of the other vectors V2, V3 up to V sub k. In other words, the vector V1 depends on the other vectors in the set. This property is characteristic of a linearly dependent set. Yeah, okay. So I guess that leads to theorem 4.8. Some of these almost seem like, what's the value of using the ink, you know?
It's not.
Yeah.
I don't think I've learned anything new over the last, the last theorem, it gave us nothing new.
Yeah.
It's exactly the same.
Let S equal V1, V2, V3, comma, dot, 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 comma, V sub k, I'm guessing. Yep. Where k is greater than or equal to 2. Okay. Is linearly dependent okay, if and only if at least one of the vectors Vj I can't write, can be written as a linear combination of the others. they do a proof here. And there is some set of C1 through CK, not all zero, such that because at least one of those coefficients must be non-zero, no generality is lost by assuming it's the, I would have said the CI one, but they said C1 is not zero, but you could do CI if you want to. Then solving for VI, if you had done CI, as a linear combination of the other produces, and basically you do your reduction almost with that. Divide by CI.
That's a 1.
Yeah, they're doing 1, sorry. C1. Because it's not zero, you can divide by it, and then you have V1 is written as a linear combination of the others. Whereas you're not guaranteed that there could be others other than C1 that are zero, but we're just assuming C1 is one of the one, even if it's the only one that's not zero. Okay, conversely, suppose that the vector V1 and S is a linear combination of the other vectors. V1 is C2, V2 plus C3, V3 plus all the way up to CK, VK. Then the equation basically here, okay. I don't care a lot for their nomenclature here. The original C1, C2, C3, and all those, fine. Then that next line, V1 is equal to minus C2 over C1, V2, you know, that makes sense. Conversely, suppose that vector 1 in S is a linear combination of the other vectors. And now they go in and say vector 1 is equal to C2, V2 plus C3. Those C2, C through CKs are not the same as the ones at the top. So why did they use them? That's the thing that kind of bugs me about it. Then the vector equation minus V1 plus all these others is equal to 0. And it has at least one coefficient, that's that minus 1, that is non-zero, so it's linearly dependent. I just don't like their use of those subscripts as if they're the same, and they really aren't. In my mind, they're not. Okay, so let's do example 12. In example 9, way back.
They're reusing stuff.
Yeah, they're using what?
They're reusing stuff.
Yes, exactly. We decided they were linearly independent or dependent. Show that one of the vectors in this set can be written as a linear combination of the other two. I guess I'll write them down. Here's S, and it's a set of 1 plus x minus 2x squared, comma, 2 plus 5x minus x squared, comma, x plus x squared. Okay. That's V1, V2, V3. All right. A couple of ways you could approach this, and I'll just look at those constants to start with. There's a 1 and a 2 and a 0. Okay. So obviously, to me, I don't know if it's true or not, but it seems like to me, 2 times V1 is going to be necessary to get that 2 there, right? Okay, so I'm going to say V2 is equal to 2 times V1. Now that will make that a 2 plus 2 minus 4. Huh?
2 plus 2 minus 4?
No, okay. No, here's what I'm saying. If you do 2 times V1, that'd be 2 minus 4. There, right? And you want that to add to be this one. Okay? So then 2x seems like it's going to have to be plus V3. Yep. I don't know if this is going to work, but this is just the first step. 2 times this one, that makes it 2 minus 4, plus that one, which is,
1 plus 1.
I'm sorry. I did that wrong. 3v3, I think. Yeah, 3v3.
V3 plus 3.
Yeah, because you see, that added and made this a 2, you need a 5 here, so you're going to need 3 from here. Okay? So now we've got the 2 right, now we've got the 5 right. Let's see, we're hoping the other comes out right. This will be a minus 4 plus 3 is a minus 1. So that did work out. Now that was
Okay, that
just
was
a real cheap way of doing it.
That was gray and fuzzy.
It was what?
Gray and fuzzy.
Yes. Okay. I just took advantage of the fact there is no constant term in that last one. And so the middle one has to be twice the first one.
Okay.
It's the only way you can get a 2 there. So start with that. V2 is twice V1. Then when you do that, twice V1, that becomes a 2, 1, negative 4. Okay? Now let's go to the second term. You got a 5 there, a 2 there, so you're going to need 3 from that of the x. Now, that's a V3 up there, not an x cubed. Okay?
Yeah.
Okay. So you need 3 of those, so let's just try 3v3. Now see if it works. Okay? Don't have anything else to play with, so you hope it works.
2 equals 2.
Yeah.
And then 2x plus 3x is 5x.
5x.
And then negative 4x squared plus 3x squared is negative x squared.
So that does work. Okay. Now that's how I did it. That may not be the easiest way. To me, that was the easiest one.
And of course, you can do this multiple ways.
You can do it a bunch of ways. Exactly.
Divide by 2, subtract, or subtract
exactly.
the other thing over, divide by 2, and you get the other.
Right. Okay. Let's see what they did. There it is. Oh, they came out the same thing. I don't know if they did it the same way, but they did. Actually, what they did was do your row reduction, and then when you wind up with something at the end, then let that be T, and back off from there, and you got it. But it seemed like that was sort of a lot of extra work to get the same result. Okay.
Yeah. And I can kind of get this too. So.
Yeah. They all may not be that easy, but that one wasn't bad.
That's probably one of the more complicated long way.
Yeah. Theorem 4.8 has a practical corollary that provides. Oh, there's theorem 4.8 on the previous page. A simple test for determining whether 2 vectors are linearly dependent. Haven't we done that?
Like I said, it's been repeating itself.
I know. 2 vectors U and V in a vector space V are linearly dependent if and only if one's a scalar multiple of the other. I mean, how many times have we seen that? Yeah. All right, so anyway, nothing new there. I'm not even bothering writing it down. Do we have time for 13? I think we do. Yeah, I thought we should have plenty of time. So I don't know if I'll need it, but I'm going to clear this. Okay. A. 12A. 13A, sorry. Here's a set, S, two vectors, V1 and V2. And they are 1, 2, 0 and negative 2, 2, 1.
Okay. So we need to find out.
What is the question? That set, they say, is linearly independent because neither one of those are scalar multiples of the other. Okay? Well, yeah, that's pretty clear to see. If the second was a scalar multiple of the first, it would have to be minus 2 times it, right? Because that first digit is.
Right.
But minus 2 times 2 is not 2, it's negative 4. So no, it can't be. Right. Okay. So those are linearly independent. Okay. Here's the B. Now they draw a picture down there and they see that they can't be, they're not a multiple of each other. The picture doesn't help me see that. I can see it without it. Okay. Here's S again, that's an ugly S, is another, again, V1, V2. This time it's 4, negative 4, negative 2, and negative 2, 2, 1.
So this time, the second, let's see, if you multiply the second part by negative 2, you get a plus 4, you get a minus 4, and you get a negative 2. And yes. That's dependent.
So linearly dependent. Okay? And when they draw the pictures, one is exactly opposite direction from the other. Now, they've drawn that in 3 space. I'm not sure I see that well in 3 space, but they do the little dotted lines there, and it helps you see it somewhatly. Okay? They are linearly. And that did finish 4.4.
Yay!
Do any odds, either 1 or 3 or both, and they have 4 parts each, by the way. 5 or 7 or both. Okay? Any of the odds 9 through 19. Any of the odds 21 through 27. Any of the odds 29 through 39. Either 41 or 43 or both. Either 45 or 47 or both. Either 49 or 51 or both. Do 53. And you can give a shot on 55 if you'd like. Do 57. And then there's a true-false 59. Take a look at that anyway. There's a proof 61. I think it's not too bad to do. And then there's some guided proofs and other proofs, any of the odds 63 through 73. All right. And that's 4.4.
Is the chicken in the cafeteria any good?
Is the what?
Chicken in the cafeteria any good?
What kind of chicken? Like grilled chicken?
They have like chicken tenders or something like that.
I haven't had those. I've had the grilled chicken salad, and it's quite good. But I haven't had the tenders. So.
I may go down there and try that out.
I've seen lots of people getting them, so I assume they must be okay. Okay, do we have time for 4 or 5?
We got 7 minutes.
7 minutes, yeah, let's try it. Basis and dimension. We came close to getting there last time when we were talking about spanning but we kind of dropped that and went into dependence and independence, which there's a reason for. You need to span and be independent. So, all right. In this section, you continue your study of spanning sets. Like I said, we got going on those and left them off for a while back. In particular, you will look at spanning sets in a vector space that are both linearly independent and span the entire space. So the two concepts we did in the last section, we started with spanning, then left that and did independence and dependence. Combine those together, now you form a basis. Such a set forms a basis for the vector space. The plural of basis is bases. It looks like bases, but it's bases. Okay. I guess it's Greek or something. To me it is. Okay. Here's the definition of a basis. I can probably get it on there, but since it's a new topic, let me go to a clean page. A set of vectors, S, and we'll name these cleverly, V1, V2, V3, comma, dot, dot, dot. Is it going to VK again? Ah, this one's going to VN.
We're not German anymore.
I guess not. We must be.
It would actually, if it's number instead of constant.
Yeah. What it may be happening is they're going to use K for something else, but we'll see. Okay. Yeah, I guess so. This set of vectors in a vector space V, okay, is called the basis, okay, for V when the following conditions are true. Number one, S spans V. Okay? In other words, there aren't any vectors in V that are not a linear combination of those vectors in S. They're just not. Okay. Number two, S is linearly independent. So basically combine, huh?
It's strong independence.
Yes, very. They declared it many years ago. Okay. All right. This definition does not imply that every vector space has a basis consisting of a finite number of vectors. This text, however, restricts the discussion of bases to those consisting of finite number of vectors. So it's sort of like we're in finite linear algebra, not infinite. Okay. Moreover, if a vector space V has a basis consisting of a finite number of vectors, then V is said to be finite dimensional. So here we've gotten our first word in this section, basis, and now we're introducing the second word, dimension. It's finite dimensional. Otherwise, V is called infinite dimensional, which we're not going to do. A vector space P of all polynomials is infinite dimensional, as is the vector space of continuous functions from minus infinity to infinity, defined on the real number line.
For those science fiction equations.
Yes, something like that. And the vector space V, which is the zero vector alone, consists of all the zero vector, consisting of the zero vector alone, is finite dimensional. Okay? I like to leave off the zeros as much as possible. Okay. Let's see if we can do example 1. Do we have time?
2 minutes.
2 minutes. Okay. I think I'll do them. Show that the following set is a basis for R3. I think this should be almost intuitively obvious. Okay. It's 1, 0, 0. It's 0, 1, 0. And it's 0, 0, 1. Okay.
This
Yeah. How you would go about showing that is pick some vector in R3, any old vector in R3, and that would have to be what you want to name it, V or U or whatever. Okay, let's call it V. So it would be V1, comma V2, comma V3, 3 components. Well, obviously,
The change would be
it would be,
the first component.
yeah, V1 times the first one plus V2 times the second plus V3 times the third. And any vector could be written that way in there. So therefore, that spans it. And then obviously, that is linearly independent because do the matrix from that, and you've got the identity matrix.
And this would still work if one of those was negative, right?
Yes. Yes.
Or if all of them.
Yes. Absolutely. Because
It'd just be that, like, negative V1, negative V2, negative V3 times these.
right. Okay. So it fits both criteria. It spans it. In fact, that's called the standard spanning set, I believe is what the name was for. And what's more, they're linearly independent of each other. Okay?
Pretty much what they were asking for.
Yeah.
And we are out of time.
We are out of time. And they call it then the standard basis for Rn. Oh, wait, no. That's the standard basis for R3. If you do the same thing for N things, 1, 0, 0, 0, 0, 0, until you get to N, and 0, 1, 0, 0, 0, 0, until you get to N, 0, 0, 1, 0, 0, 0, you know, until all those, they call those E1, E2, E3, up to En. That's the standard basis for Rn.
It's funny because the true false in the homework for the last section, they
Right.
asked if it was like, if this code, this was a spanning set of R4, and 1, 0, 0, 0, and then 0, negative 1, 0, 0, and then 0, 0, 1, 0, and 0, 0, 0, 1.
Yeah.
That's kind of why I asked the question. So
Yeah. And yeah.
I figured it would be.
Yeah. Has,
Spanning set.
yeah. So let me mark the roll. AA. All right, I already had you here. So let's